The purpose of this video is to review the use of the TI84 family calculators for computations on the normal distribution or bell curve. We'll start with the standard normal distribution, that is the normal distribution with a mean of 0 and a standard deviation of 1, so the z-scale is actually the standard deviation scale. So almost the entire curve is found between 3 standard deviations below the mean and 3 standard deviations above the mean. So let's do some calculations with the TI calculator. So first of all, the normal distribution functions are found under the distributions menu here. So we do second distribution. And the one we really want to use to start with is normal CDF. It stands for the cumulative distribution function, which represents the area under the curve. And that's what gives us probability, not the height of the curve, but the area under the curve between 2 points. So we'll start with this problem, finding the area between 1 standard deviation above the mean and 2 standard deviations above the mean. You simply select normal CDF and put in 1, 2, close parentheses, to make it look nice, and hit enter. It tells us that that area is 0.1359, or about 13.6% of all the area on the standard normal curve is held between those limits. So that's our first problem. For our second problem, this will remind us of the empirical rule. We want to go from 1 standard deviation below the mean to 1 standard deviation above. Hit clear. Second distribution, normal CDF. -1. Remember, to do negative numbers on the TI calculator, use this negative sign, not the subtract button. So -1, 1. And that should give us, of course, 68%. And in fact, it does. 68.26%, or 0.6827, actually, if we round in the fourth place. We can now find out where the second step in the empirical rule comes from by considering what's the area between -2 and 2 on the z, or normal, standard normal scale. So clear. Second distribution, normal CDF, -2, 2, and of course we should get 95%, because that's the empirical rule. 95% of all the values fall within 2 standard deviations of the mean. And there it is, 95.45%. Finally, we're reminded that exactly half of the values fall above the mean. On the standard scale, of course, on the z-scale, the mean is 0. So if we go from 0 to essentially forever, we should get 0.5. Well, let's try that with going from 0 to only 10 standard deviations above the mean. Second distribution, normal CDF, 0, 10. And notice I get almost 0.5, 0.4999995. And in fact, no matter how high I go, I'll get the same answer. Because of the way the TI works, but rounded to the 4th, 5th, 6th, 7th, 8th, 9th, or 10th place, that's 0.5. Okay, so that's the standard normal distribution, the one where we're essentially working on the standard deviation, or z-scale. Let's move to the more general distribution, where we have a specific mean and standard deviation. The one plotted here is with a mean of 140 and a standard deviation of 20. So we can always convert from the variable natural scale, like this one, back to the z-scale using the formula we showed in class. My z number, or standard deviation number, first I take the value, subtract the mean, that gives me the distance between the value and the mean, and then I divide by standard deviation, the size of the standard deviation, to move from the x scale to the z scale. Let's do that for this first problem that's highlighted here. Find the probability that a value will fall between 130 and 165. So first I'm going to convert these numbers to Z numbers, and then I'm back on the previous page. I'm going to use parentheses so things go right. 130, that's the value, subtract the mean of 140, and then divide by the standard deviation, which is 20. And it says that this value lies at minus 0.5, or half a standard deviation below the mean. And then I can convert the 165 in the same way, from the X scale to the Z scale. So I take parentheses 165 minus the mean 140 and divide by the standard deviation. And that says 165 lies 1 1/4 standard deviations above the mean. 25. So now I can solve this problem using the technique on the previous page. Second distribution, normal CDF, from negative 0.5 up to 1.25. So 58.58% of the values fall in that range. But as noted on this page, if you don't specifically need to move the problem from the X scale to the Z scale, then we can use the extended form of normal CDF, where we put in the lower limit, the upper limit, the mean, and then the standard deviation. So let's clear this and do this problem directly. Second distribution, normal CDF, I put in 130, that's my lower limit, 165, that's my upper limit, followed by the mean and standard deviation. 140 is my mean, and the standard deviation is 20, and I get, of course, the same answer. So that's the more direct way of computing the area. Similarly, we can find the area between 100 and 180, or the probability that I get a single value in that range, with second distribution, normal CDF, 100, the low limit, 180, the upper limit, the mean of 140, and a standard deviation of 20. And it says that 95.45% of the values fall in that range. That number should be familiar. Well, actually, 100 is exactly 2 standard deviations below the mean, and 180 is exactly 2 standard deviations above the mean. So that's my empirical rule working again for me. How about the probability that X is bigger than 180? Well, there's a couple of ways to attack this. The most direct way, if I want to be larger than 180, 180 is my lower limit, so I do second distribution, normal CDF 180, comma, forever. Well, where is forever? 200 isn't far enough. We have to go much further, so I'm going to go all the way to the biggest number that the calculator knows. That's 1, and then second of the comma is important for use. So second of the comma is double E, and then 99. So that's 1 times 10 to the 99th power. That's the biggest number the calculator knows. And then comma, the mean 140, and the standard deviation of 20. And that will give the probability of finding X anywhere bigger than 180. 180 essentially to infinity. And I'm going to write this one down. There's a nicer way to do this, however. If we want the probability that X is bigger than 180, up here, well, we know that there's exactly 50% of the distribution, or 50% of the values are above the mean. So we can simply take the 50% that I know is here and subtract the part that I don't want. And let's see how that works. Clear? So I take 0.5 and subtract the part I don't want, which is the part from the mean up to 180. And of course I get the same answer. About 2.28% of the values fall in that range. Okay, so we're almost completed with what we need. There's one more thing that's often done with the normal distribution. Instead of giving specific limits and asking what the probability is, sometimes I want to give the probability and get the limit back. This is the job of the function INV-norm, or inverse normal distribution. It takes in the probability or proportion that I want and the mean and standard deviation, and gives me the upper limit. So suppose I want the 90th percentile. I do second distribution. INV norm is the third entry in that menu, just below normal CDF. I put in not a percentage number, but a probability or a proportion, 0.9, that's 90%, followed by my mean, 140, comma, standard deviation, 20. The number I get, 165.63. 10. That says that 95% of the distribution, or 95% of the values, will be less than 165.63. And this is often used, for example, in deciding when I want to keep only the best 10% or the best 5% of a group. Okay, well, that concludes the lesson on basic use of the TI-84 with the normal distribution.